Hi, this is Mrs. Rutchling. We know that solids have particles close together, so their densities are high, especially in comparison to gases. Because particles are fixed in place, they keep their shape and they keep their volume. They're not easily compressed because they're so close to one another. They have strong intermolecular forces compared to the energy that they have. The energy is not enough to separate or even allow the particles to flow. Even though the molecules are fixed, they do vibrate in those points. Two general categories for solids are crystalline and amorphous. Crystalline, our particles have a highly ordered arrangement. You can see a pattern. Amorphous is where there's no order. It looks more like a hot mess. Breaking down crystalline solids, we look at the lattice and what is at each point. You can almost think of this as a graph and what is at the point. If it is a molecule, for example, water, then the units at the points are molecules and it's a molecular solid. It has a low melting point. If there are ions at the composite points, then it's an ionic solid. Those have a strong attraction, so they have high melting points. If there are individual atoms at the composite point, then we call those atomic solids. Sometimes you will hear them called covalent network solids. Melting points vary based on how they are held together. Looking then more closely at atomic solids. If they are held together by covalent bonds, atomic solids have atoms at the point, and they have a variety of melting points. You can't say general melting point information about atomic solids. Breaking down atomic solids further, if they're held together by covalent bonds, that's a very strong force and they have high melting points. If they are called non-bonding atomic solids, they are held together by dispersion force and these have low melting points. Lastly, metallic atomic solids are metals that are held together by metallic bonds and they have variable melting point. Covalent atomic solids are often called non-bonding atomic solids, are held together by dispersion forces. Atoms that are in non-bonding atomic solids have stable electron configurations, so they do not form covalent bonds. Since they are held together by those relatively weaker dispersion forces, they have low melting points. In a metal, we have the nucleus and the core electrons. They're often called cations because they have an overall positive charge. The valence electrons, or the free electrons from the outer shell, are free to move. They are not localized. We call them delocalized. It's often called an electron sea because if this electron moves, then it repels all of these and they move away in a wave pattern. Water is unique because it is less dense in the solid state than in the liquid state. We see evidence of this all the time when we see ice floating in our water. Why is that? Hydrogen bonding creates space in the solid or in ice, whereas the liquid water, the molecules are very close to one another. It's a good thing that solid water is less dense and floats. Aquatic life survives because the lakes freeze from the top and there is space for them to survive, both animals and plants at the bottom. What effect does increasing the temperature have? Increasing the temperature allows these particles to overcome their intermolecular forces and start to move around and become closer to one another. Pause and try to fill in this diagram. When intermolecular forces are weak, volatility is high. It doesn't take much for those particles to separate and they easily become a gas. If they easily become a gas, that means there are more particles to hit the sides of the container and the vapor pressure is high. The boiling point is low because it doesn't take much energy to separate weak intermolecular forces. An example of this, an example of a liquid with weak intermolecular forces is acetone. On the other hand, if intermolecular forces are strong, the volatility is low, and because there aren't many particles that become vapor, the vapor pressure is low. It takes a lot of energy to separate strong intermolecular forces, and so the boiling point is high. And an example of a liquid is water with that hydrogen bonding. Pause the video and try these problems. Ionic bonds tend to have higher melting points than molecular solids. That part is true, because ionic bonds are stronger than the intermolecular forces that hold molecular solids together. That is a true statement. Which of the following solids would have the highest melting point? We need to look at the type of intermolecular forces. Sodium metal has metallic bonding. Table salt is ionic. Cotton candy is sugar, which means it is molecular. It has intermolecular forces. And graphite is an atomic solid. Of these, the ionic bond is the strongest, and they would have the highest melting point. Cotton candy is made of sugar. So we can say that it is not a covalent atomic solid because it is molecules. It is not a metal. We need to decide between crystalline and amorphous, and because it is spun in random patterns, it is an amorphous solid. Looking again at the picture, what kind of solid is depicted? Well, this is crystalline, so that means we can eliminate amorphous, metallic, and covalent atomic. It is an ionic solid. Here we have atoms at every point, so we can eliminate ionic solid because there's nothing that indicates that those are ions. Because it has a regular pattern, we can eliminate amorphous. Because it is atoms, I'm going to say that it is a covalent atomic solid. Pause the video and try this one. Metallic solids have delocalized electrons. Electrons can move. This actually is what electricity is, electrons moving. So metals are good conductors of electricity. Pause the video and try this one. Covalent atomic solids are harder than molecular solids. That is true because covalent atomic solids are held together by intermolecular forces. That is not true. And molecular solids are held together by large networks of covalent bonds. The reasoning is reverse. Covalent atomic solid is held together by large network of covalent solids. So although the first statement is true, the explanation is false.